Okay. So today's last speaker is Jerome Quintin from University of Waterloo and Perimeter Institute of Theoretical Physics, Canada. And he's going to talk about fingerprints of a non-inflationary universe from massive fields.
Okay, so thank you, first of all, for the invitation. I'm happy to get this opportunity to present my work today to you. And yes, I'm gonna jump into this topic first by having a fairly broad overview and introduction. So before I start, I'll say that this is mostly based on recent work from a few months ago, jointly with Xingang Chen and a grad student, Reza Bahadi. So you might see the names popping up, but I won't put the reference all the time. I'm just putting it here to start. So I'm gonna start by sort of reviewing what we know about the very early universe and emphasizing what we know very well versus what we might know less well. So I particularly like this picture here. So this is Planck's reconstruction of the primordial power spectrum for the curvature perturbation, the primordial curvature perturbation, as a function of scale. So as a function of inverse wavelength of these primordial fluctuations. And the observations are telling us that over a certain range of scales, this primordial power spectrum is almost independent of K. So in this interval here, we almost have a horizontal line. So what we do often is that we fit this with a power law. And at this point, we have a very good measurement of the amplitude, so the height of this curve, the height of this power law, and its tilt. So its inclination with respect to being just a horizontal line. And that's really amazing. But at this point, those are almost the only two numbers that we know with confidence that we've measured, different from zero, different from a null hypothesis. And already at this point, we could ask, how do we explain this? Let's step back and say, what kind of scenario for the very early universe could lead to this kind of power spectrum? So the picture that I like to show then is this following picture, where we think of the horizontal axis as being time, specifically conformal time, for example. And then at some late time, we observe the cosmic microwave background. And that's how we can reconstruct the primordial power spectrum. That's how we can infer it thanks to these observations. And what we infer is that there must have been some kind of primordial fluctuation, like the curvature perturbation, that was before producing the CMB in a way, was on very large scales. So on scales larger than the horizon, such that we can actually have a causal explanation for the origin of these fluctuations. So there would have been some kind of initial conditions at some very early times. These fluctuations would have all had the same kind of origin. They would have evolved, they would have exited the horizon, frozen on large scales, acquired the spectrum that we infer, to then later re-enter and lead to the oscillations and the anisotropies in the CMB. And so the question of what kind of scenario can give this picture becomes a question of what scenario can give a contracting co-moving horizon here on the left at early times. And let's just review the math as an exercise. So the co-moving horizon is 1 over the scale factor and the absolute value of the Hubble parameter. And we can ask, when is this shrinking as a function of time? So we take the time derivative and we ask when it's negative. And we can do a few lines of calculus and see that this is related to the quantity 1 minus epsilon, where epsilon is related to the time derivative of the Hubble parameter. Or equivalently, if we use the Freeman equations, This is related to the equation of state parameter W, so the ratio of the pressure to the matter's energy density. And we've got a different sign depending on whether our Hubble parameter is positive or negative. And so asking this to be negative can then be translated into saying that we either need this equation of state of matter to be sufficiently negative when H is positive, or vice versa, we need W greater than -1/3, so pressure has to be sufficiently large, and negative Hubble parameter. This can furthermore be translated into conditions on, say, the scale factor alone. So this would be like, the first line would be acceleration and expansion, or the second line would be like deceleration and contraction. So here at the bottom in words. And so this has led to, on the first line, the paradigm of primordial cosmology, namely inflation. And on the second line, we get an alternative, a so-called bouncing cosmology. So the idea there is that the contracting moving horizon is coming from a contracting universe, simply. And that's when the perturbations would have been generated. And then there would have been a bounce, so some kind of transition from contraction to expansion. And then after the bounce, we would have had standard Big Bang cosmology without inflation. Let me point out, by the way, that these requirements on, say, W and H or the scale factor, they're the same that would give you flatness. So we know inflation explains why the universe would be flat. Same thing with a bouncing cosmology. Okay, so we get the two contending scenarios already. So on the left here, we know quite well inflation. On the right, we know a bit less well the alternative, the contracting bouncing cosmology, but there's been some work. I'm obviously not citing everything. There's thousands of papers. But I'm just pointing out that I've spent quite a bit of time on the right column. So that's why you'll see me talk more about this for the rest of this talk. But I also work on inflation, and I always strive to find ways of being able to really differentiate, tell apart scenarios. So yeah, so far I really only described the background evolution, but now we have to revisit the perturbations. How do we explain the power spectrum? How do we explain the anisotropies in the CMB? So I'm going to take again a very kind of generic approach to presenting this. So I want to give just a very high level description of what can happen. So I'm going to say that we have a very general theories. It could be GR, it could be modified gravity. We could have one field, we can have several fields. We could have a canonical scalar field, or something a lot more complicated, a chaos sense, a Horndeski, whatever. In many of these situations, not always, but in many situations, we can then find a degree of freedom whose which I'm going to express in this form here. So this is the action expanded to second order, and it's describing a scalar degree of freedom, V sub s. It's some kind of normalized fluctuation variable. And it's then described by this action. And what is key here is the time dependence of this term here. So the variable z is some potentially very complicated time dependent function. But for many, many theories, the action can be reduced to this form. And then if this z second conformal time derivative, so double prime over z, is given by this expression here, so 1 over conformal time squared with some approximate constant at the top, then the solution is fairly well known. It's like a Hankel function of the first kind that would reduce at early times on early times on small scales to something like a quantum vacuum, and at the opposite regime at late times and on large scales would give us a power spectrum for this scalar degree of freedom that would be almost invariant on scales, so almost scale invariant. So if this index nu here is almost 3/2, then the dependence on k is almost vanishing. So this is very, again, high level, but now let me give a couple of examples. So now let's be specific. Say we have general relativity. We're assuming a bunch Davies vacuum initially. We're going to take only one scalar field, minimally coupled. And furthermore, we're going to say that we have a background with a constant equation of state, or matter with a constant equation of state, an average at least, and also a constant sound speed, another thing that could enter into these equations. When we have all of this, then this variable z will simply be proportional to the scale factor. And then this z double prime over z just becomes this a double prime over a, and asking near scale invariance is like asking this to be approximately equal to 2 over conformal time squared. And now there are two solutions for this. Either the scale factor is inversely proportional to the conformal time, or it is proportional to the conformal time squared. And the first situation is that of near de Sitter expansion. So in physical time, that would be near exponential expansion. Certainly, it's very fast expansion, it's accelerating expansion. And the other situation is matter domination. But remember, if we have an equation of state that is large, for this to have a contracting comoving horizon, then we have to be in a contracting cosmology. So this would work only if we were in a matter-dominated contracting universe. So it's like having a fast contraction. And this kind of duality has been known for some time, but it's already interesting, and it's certainly pointed out the fact that it's not getting a near scale invariant power spectrum is not unique. Inflation can do it, but it's not the only way. And again, I'm stressing that this is, with these assumptions, those are two examples, but you can modify any of those. You can modify your gravity, your scale of field, your equation of state, your sound speed, and so on. And then there's many other ways in which you can generate perturbations that, in principle, at least, could explain the power spectrum that we infer observationally. Now, not all of them are consistent, though. And what I'll say at this point is that there are, I mean, we can sort of classify at least the scenarios in different categories. So inflation would be all the models that are inflationary. So they're expanding rapidly, they're accelerating. And then you can have contracting scenarios like the matter bounce. So this matter-dominated universe followed a contracting universe followed by a bounce. This would be a situation of a contracting scale factor and a rapidly contracting scale factor. Excuse me. Then you also have the possibility of an expanding universe that expands very slowly. This is known as genesis. So you start very close to Minkowski, and you slowly have a universe that slowly expands. And finally, you can have something that's known as ekpyrotic cosmology, or process, where the universe is contracting, but this time at a very slow rate. So in all of these categories, there are models that work. So I've got more material if you want to see in my extra slides, but for now, I'm just going to leave it at that. Of course, they all come with caveats. And we know very well all the models of inflation that work, less so for the alternatives. But yeah, at this point, you just have to take my word that some of them can in principle work. Now, when what I want to put forward is that, yeah, besides potential theoretical strengths and weaknesses, we would hope to have some kind of observations that would allow us to really distinguish these different scenarios for the very early universe. And I presented so far what we know about the 2-point function, so the power spectrum. We know very well its amplitude and its tilt. But at this point, everything else is consistent with 0. So in particular, we haven't observed any primordial gravitational waves. So we only have an upper bound on this tensor spectrum. And we haven't measured any higher correlation functions like non-Gaussianities. They're all consistent with 0 at this point. Now, let me say that it's not a bad thing necessarily. We've learned a lot with these constraints already. They already put a lot of they're already constraining many models of inflation, for example, but also constraining a lot of the alternatives. And certainly some inflationary models have been ruled out, and some alternative models, like some models of bouncing cosmology, have been ruled out. But there are still many remaining that are consistent with all these numbers. And there's a hope that, for example, to give one example, if we measure the tensor to scalar ratio in the near future, perhaps this could be a strong indication of inflation versus an alternative. And maybe this is true, but you could also argue that you can come up with an alternative that would also explain this. But the other way around also, if in 40 years from now, I don't know, but in a fairly long time, we still haven't measured any primordial gravitational waves, and we keep lowering our bound on R, just lower and lower and lower down to the best kind of sensitivity we could hope for with the best telescope and whatever, then some could say, well, that's bad for inflation. Inflation usually predicts a fairly high tensor to scalar ratio. But even that is not necessarily true. Even in inflation, you can predict a very, very small tensor to scalar ratio, and potentially as small as you want. So yeah, if you compare this with an alternative that would essentially predict almost no primordial gravitational waves on cosmological scales, then you still be faced with the fact that you're not able to tell them apart because they would lead to the same predictions essentially. So I'm trying to show this to really motivate that it might not be enough with just these numbers, and we want to do better. And specifically, we want to have more things to try to look after. And what I'm going to propose is to add massive fields to our theories, and see. And I'm going to present and argue that the signatures of these massive fields could tell us a lot about the actual primordial scenario for the universe, the early universe. So what we do in cosmology is when we compute our primordial perturbations and we compute their correlation function, we're sort of doing some kind of Feynman diagram, but slightly different. So to compute, for example, the 2-point function that would give us the power spectrum, what we have is like the interaction between two zeta fluctuations. And these fluctuations are sort of emerging out of the vacuum, and we're measuring them on some surface at a late time. So for example, the reheating surface that would set the end of the primordial phase and at the beginning of standard Big Bang cosmology. And this is really an in process. So contrary to a standard Feynman diagram where you have like an in state and then an out state so you prepare something and you measure that later times. Here it's more like an in situation where you could imagine starting on this reheating surface and going down here so you've got your in state, and then again you go back up to your in state again. So the so-called in formalism is usually used to compute, for example, the 3-point function, so to evaluate non-Gaussianities. But it can also be used more generally whenever you have some kind of interactions. So that's why I'm introducing it here, because what we want to do now is to add some interaction with a massive field. So we're going to call this field sigma. So we're going to postulate that there's this field and that it couples to our primordial fluctuations zeta here. So sigma couples to zeta in such a way, for example. And if so, then the expectation is that our correlation function for zeta that we measure, that we observe, would not be just the standard one that we had in the picture at the top, but also something with a correction coming from the fact that we have this interaction with sigma, with the massive field. So to understand how this happens, we're just going to revisit how it is that these respective fields are evolving at early times. So first, regarding the cosmological fluctuation. So if you go sufficiently back in time, it's going to start in some kind of vacuum state. And then it's best to describe it by writing the metric as being proportional to Minkowski space. So here the scale factor is just a conformal factor to the Minkowski metric, and tau is the conformal time. And when the metric is written this way, it's fairly straightforward to write down the equation of motion for the cosmological perturbation zeta here in Fourier space at sufficiently early times on sufficiently small scales. And the solution to this harmonic oscillator in conformal time tau is just an oscillating function like this. So this is, for example, the usual Bunch-Davies vacuum. Now, regarding massive fields, they are best described when writing the metric in physical time. So here, t would be the physical time. And now the equation of motion for a massive field on this background is a harmonic oscillator in physical time again at early times for a large mass. And then the solution to this harmonic oscillator is again just oscillations, but this time where the frequency is given the mass, contrary to here where it was the wave number k. And also the oscillations are in physical time as opposed to being in conformal time here. So we can already see that the relation between the two is the scale factor, because that's what relates the conformal time to the physical time. That's what relates the transformation of the metric. And to see how this then translates into a signal in the power spectrum, we can use the actual Innen formalism. So what we do is that we write our correlation function for zeta with interactions as being the sum of the correlation function without interaction. So in the free theory, so that's the usual power spectrum without any massive field present, without any interactions. So just the standard power law. And then there are corrections to this coming from the interactions. So for example, that could be parameterized by an interaction Hamiltonian. And this is going to give a correction to the power spectrum. And to give one specific example, so we could get a correction that would be given by a time integral of an interaction term of this form, for example. So if there's some kind of sigma zeta squared interaction in the Hamiltonian, then we can have something like this here. And now this time integral becomes an integral in some oscillating function. So sigma we just saw is oscillating in with frequency given by its mass and in physical time, and zeta is oscillating in its the frequency is its wave number and in conformal time. Now this is a highly oscillatory integral. These are very large arguments in these oscillating functions. So in the average, such highly oscillating integrals are just zero. And that's why we usually say that we can ignore heavy fields when we're dealing with low energy physics. We can ignore these heavy fields in our low energy effective theory. So we integrate out these heavy fields. In other words, we actually integrate them in our path integral, and then their contribution is just zero because their integrals average out to zero. Now, here this is potentially not true anymore if there's some kind of resonance in this integral. So because these are oscillating but with different kind of frequencies, there can be a point where the frequencies actually match. And when this happens, when we have a saddle point to this integral, then there can be resonance, and the integral would not be zero anymore, and there'll be an actual signature of this resonance in the correlation functions. And this resonance happens when the mass of this heavy field is equal to twice the wave number of the primordial fluctuation divided by the scale factor at that resonance time. So we see the scale factor appearing here. And just dimensionally, it's natural for it to appear there. And we can start seeing how that might be useful in to be able to determine what was the actual evolution of the primordial universe if we can measure such a signal. So to give a concrete example, so if we take our scale factor to be a power law of time, then doing the calculation a bit more carefully, we get a sine of k with a power. So we've got a k-dependent frequency whose power depends on this p. So the p is precisely what entered was telling us about the scale factor evolution. So we get oscillations whose frequency and also the amplitude. So just the calculation wouldn't give you the amplitude, but a more careful calculation would give you also the amplitude and would also depend on p. And we can start seeing how, for example, if we have a very large p, so something like an inflating universe, we're going to get a signal, so a correction to our power spectrum that is oscillatory and with a frequency dependence and an amplitude dependence that looks like the plot on the left. Versus if we have a very small p, so something like a very slowly evolving scale factor, so a slowly evolving contracting universe, for example, we're going to get a completely different kind of signal. So we're going to get something where the frequency dependence and the amplitude dependence is kind of opposite of inflation. And at this point, this is a very generic presentation. I'm not really assuming anything about the models. I'm just saying this would be the expectation, very generally speaking. And if true, then it really has a potential of being able to tell apart inflation from a bouncing alternative, for example. Now, let me just say that this has been coined differently in the literature. So for example, for inflation, the idea of having massive fields interacting in a background at energy h is like having a collider at fixed energy. So it's been coined a cosmological collider. And also in a contracting cosmology, we kind of have a different situation where we don't have a background of a constant energy. Instead, our Hubble parameter in absolute value is growing. So as the universe contracts, we're going to higher and higher energies. So the interactions with massive fields is kind of different. And in particular, we can have interactions with different masses, fields of different masses across time. So it's more like having a particle scanner instead of having a fixed energy collider. So yeah, this term of particle scanner has also been coined in the context of a bouncing universe. And here's just a little sketch that we made for a paper of sort of depicting this resonance process where you can imagine having a massive field that's oscillating here in cyan, and in orange we have the primordial fluctuation. There's going to be a point where the frequencies are going to match, and when this happens, then we get this resonance and we get this correction to the primordial power spectrum. And what this picture shows is that depending on, well, we can have different k values that are going to resonate at different times. So that's one thing. So we get a resonance pattern as a function of k. And also, if we have fields of different masses, we're also going to get resonance at different k values. So we could also have different signals for different masses. All right, so now in the remaining 10, 15 minutes or so, I'm actually going to get into the what we did. So in particular, how do we model this and what kind of results we got? So how do we model massive fields? So generally, we don't really know what are degrees of freedom at high energies. For example, inflation, we usually assume something fairly simple, but the reality might be more complicated. We don't necessarily know. You could have your favorite theory of quantum gravity, try to get a potential for your fields from first principles, but that's very hard. So the kind of postulate we're going to take is that we happen to live in some kind of corner of this landscape where we can have a successful realization of the primordial scenario we're interested in. But it might not just be a standard straight trajectory. There might be some kind of valleys where there are some turns and twists in the field evolution. So this kind of picture has been used to construct to embed massive fields in inflation before. So for example, you could imagine a field that slowly rolls and then it sort of falls into a valley, and in doing so, it excites perpendicular direction to the adiabatic trajectory of inflation, and this perpendicular direction is like a massive field. So this slope here, is potential, is a massive field that oscillates as a function of time. And now we essentially use the same idea now to construct this in an alternative. So for example, we can construct a slowly contracting universe with a steep potential. So it's kind of the opposite of inflation, where you need a very flat potential to get fast acceleration. And here, so the field will be fast rolling down its potential, and then there could be some kind of bend, some kind of turn in the valley that excites a perpendicular direction. And then you've got a massive field that was excited this way. And I think this has kind of a nice analogy just from classical mechanics. Now, there's been quite a bit of phenomenology for this in inflation, which I won't review at all, but I just wanted to say that, yeah, there's been quite a bit of work. And we finally did it for a non-inflationary alternative. So the idea was there, but it had never been done for an actual alternative. So we did it now for an ekpyrotic, in the context of an ekpyrotic scenario, so a slowly contracting universe. And yeah, because I only have 10, 15 minutes, I'm gonna maybe skip the fine details of the modeling and just sort of describe the big picture, where if we take again this idea from field space, the idea is that we could have different kinds of couplings. So we could imagine having a straight trajectory and then having just a short interaction, a coupling that turns on, but only for a short period of time. So this is like having a bump in the coupling that just excites the massive field, but then you go back to the straight adiabatic trajectory, and your massive field has been excited, but it's not interacting with the background field anymore. Whereas you could imagine having a plateau kind of coupling, so a longer interaction, a longer turn in field space, or a step. So you have no coupling, and then at some point you have a coupling, and the coupling remains. So you always have, from that point onward, you always have a turning trajectory in field space. And also, let me say that I'm actually going to focus now only on the bump case. So in these situations, we can do the modeling, we can solve the equations, but it just turns out that you can excite the massive field, and your background can remain stable at least for some period of time, but it's just not as well behaved as the bump case. So yeah, I'm going to focus on this situation, just a lot cleaner. And yeah, so here are examples of results that we get with the bump case. So what is this showing? Let's focus on the plot for now. So this is a plot as a function of time, if you wish. So this is the some generalized e-folding number related to the evolution of the scale factor and the Hubble parameter. And then we got plots of the massive field. It's the equation of state, if you wish, and delta here means the correction to the equation of state due to the presence of the massive field. So this would just be a constant if there was no massive field, but now with the massive field, there are corrections to this. This is a correction to the Hubble parameter and a correction to the background scalar field. And for different values of P being the scale factor evolution. So this is all slow contraction with different values of P, or equivalently different values of epsilon. And what we see is that the model works well in terms of exciting this massive field that's at different points. in time, and then you get these oscillations of the massive field until they freeze out, because we have a contracting cosmology. These fields are heavy at early times, so they can oscillate this way. They're heavy with respect to the background Hubble scale, but as the background Hubble scale rises in absolute value, because we're contracting and we're going to high energies, these fixed mass particles end up being light with respect to the background. So that's why they freeze at some point. And then these oscillations of the massive field induce some oscillations on the background. So like on the equation of state, the Hubble parameter and the scalar field, but these are all relatively small corrections. So the background, this massive field is really like a spectator. It's not affecting the background much. And we've got some analytical understanding of all of this. And in fact, this is actually the simplest situation. And for example, the solution at sufficiently early times is just like a sine function with some time-dependent amplitude that depends on this equation, the state, on this power of the scale factor p. So this is for the background. And again, for the perturbations, I'm gonna skip the analytical bit and show the numerical results. If we have more time, I can go back at the end. But so from the example I just showed of this massive field being excited with a so-called bump coupling, now we can compute what is the power spectrum. So more specifically, what is the correction to the power spectrum compared to just a standard power law due to the interactions with this massive field. And we get this picture here where we have oscillations in the power spectrum, and the very large oscillations here on the right precisely correspond to the so-called clock signal. So this is the signal that I introduced in the first half of the talk. So this is precisely the kind of signal that we would expect from the massive field, and that would be a very clear signature, a clear fingerprint of a slowly contracting universe. So this would not be reproducible in inflation in any way. So that's very neat. That's a very clean prediction. And that's not all we see in this plot. So in particular, we also see some kind of secondary oscillations, which are much smaller in this case. And these are called the sharp features. And they just correspond to the fact that as our field is rolling down and we suddenly have a turn in our trajectory, initially there's a displacement in our massive field. So there's an initial displacement in this perpendicular direction. And this sharp turn, this sharp transition to start induces oscillations by themselves. So these secondary constant frequency oscillations, they're just due to this. And this is completely model. This is always present. That's what I want to say. So this is present in the alternatives. This is also present in inflation. So this is not a signature in any way of the actual scenario. So in terms of finding something that could really tell apart scenarios, this is more of a nuisance, but it is nevertheless there. When we implement a massive field being excited this way. Now we can explore how this changed when we changed our parameters. For example, if we lower the mass of our field, what we see is that the window over which we have these oscillations is sort of reducing in k-space. And because of this, we have fewer and fewer oscillations of this massive field. And also the relative size of the clock signal with respect to the sharp signal is sort of changing. So we've got a smaller amplitude here and a bigger amplitude in the sharp. To an extent, I keep lowering the mass here to an extent where we can get to a point where there's almost no clock signal anymore and only some tiny sharp feature. But we do notice something that's always present, and numerically at least, which is some kind of offset at large K. And this is solely due to the fact that because our massive fields eventually freeze in our background, because they're heavy initially, but they become light after crossing the horizon, they freeze, and this just shifts the height of the power spectrum compared to when there was no when the VEV of this massive field was just zero initially. So we get this shift always. And yeah, I can just quickly flash because I think I'm entering overtime. So we can also play with different things like the transition sharpness. So we can turn in field space with different sharpness. So what I was showing you was for very sharp transitions. So the top here would be very sharp, and that's when we get a very clear signal of the clock signal. Whereas for very smooth transitions, so slower, less sharp transitions, we get something that's a lot more complicated. We always have the signal. It's always present. So if you look at this reddish curve at the bottom, we always have the signal. It's still there, but its relative amplitude compared to the sharp feature signal has completely changed. And it becomes a lot harder to distinguish this signal from the rest. This is more examples of this. And again, these are more examples, just showing also the effect of the coupling versus just the induced oscillations at the background level. But I will just jump to my summary. So what we achieved, so we embedded massive fields in an alternative to inflation, specifically in a slowly contracting parodic cosmology. We managed to excite these fields in a stable way. This works best if the coupling goes to zero, namely if we have something like a bump coupling that some kind of sharp turn in field space. Otherwise, it's more complicated. And when this happens, then we confirm that we really get a nice clock signal, and we all have a much better appreciation for how this connects with the sharp feature signal and how this depends on the sharpness transition and the other parameters at play. And yeah, the main conclusion is that we've got an actual realization that shows that this is potentially an observable that could tell apart inflation from an alternative, specifically a parodic cosmology in this case. And there's still a lot to explore. This is sort of a first step in this direction. We could think of many other ways in which we could implement these massive fields. We're looking forward to trying to fit this to data, go beyond the 2-point function. So look at the biospectrum, look at the full quantum effect, and so on. So I'm going to stop here and take questions.